This is Honors Algebra 2 Pre-Calculus. We're doing Chapter 5, Section 6 of Algebra 2, and this is our first video on quadratic equations and complex numbers. So let's start by talking about the discriminant. So the discriminant is the thing under the square root in the quadratic formula. So if we just take a second to write our quadratic formula real quick. So remember, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, right? The discriminant is this thing right here, the thing inside the root of the quadratic formula. So the trick is that looking at that root, so looking at the inside of the square root in the quadratic formula, we can figure out a couple pieces of information. So the first one, right, the first one is that if b squared minus 4ac, the discriminant, let's actually start here, is equal to 0. Well, if that were 0, what we'd be looking at is we'd be looking at x equals negative b plus or minus 0, which is just 0, over 2a, which means that we get what's called a double root. We get the same root twice, because technically you'd get x equals negative b plus 0 over 2a, and you'd also get x equals negative b minus 0 over 2a, but both of them are the same root, so we get a double root, right? And you'll see that here. It talks about how there's a double root. Now, if this quantity, so let's talk about what happens if the discriminant, b squared minus 4ac, is greater than 0, then what that means is you're going to have two real roots. So if b squared minus 4ac is greater than 0, then you're going to have a graph that has two real roots. Like maybe it looks like this, where there's a root here and a root here, right? Or maybe it looks like this, right, where you have two roots here, but it's going to have two real roots. And just to show you in red what that first double root equation is going to look like, if you have a double root, what it looks like is something akin to this. Your graph goes down and touches the x-axis but doesn't cross it, right? Or your graph comes up and touches the x-axis but doesn't cross it. That's what a double root looks like. The math term for that is actually kisses the axis, which is fun because you can say things like kiss my axis and you're not actually saying anything wrong. Let's switch a different color. So if the discriminant, right, b squared minus 4ac is negative, well, now what we're looking at is we're looking at this thing inside a square root being negative, and what that's going to mean is that your graph has no real solution. So if b squared minus 4ac was less than 0, then you have a negative inside this root, and you can't take a square root of a negative in the real numbers. Like, that's not possible. If I ask you what the square root of, let's say, negative 25 is, the answer is non-real. So what that's going to look like graphically is a graph that never crosses the x-axis. Either it's a smile, right, and it's above the x-axis, or it's a frown and it's below the x-axis, but see how it has no real solutions, right? No real visual zeros that occur on the graph. So let's go ahead and walk through how this is going to work. So we're going to find the discriminant of each equation and determine the number of real solutions. We're not asked to find those real solutions, just determine the number. So in example 1a, right, this is my a, b, and c. Remember, I'm just finding b squared minus 4ac. So b squared minus 4ac is going to be a 16 minus a 4 times a 2 times a 1, right, which is 16 minus 8, which is greater than 0. So the discriminant here is an 8, right? So there are two real solutions, right? I don't know what the graph looks like, but I know, like, I don't know specifics about the graph, but I know that this is a smile because the positive 2, so it's going to look something like this. It's going to have two real solutions, right? So if you needed the visual, you weren't asked for it, but if you need the visual, that's what the visual would look like. If we go ahead and do the second one, right? Second one, here's my a, my b, and my c, right? So b squared minus 4ac is going to be a 16 minus a 4 times a 2 times a 2, which I'm pretty sure is 16 minus 16, or 0. So my discriminant is 0, which means that there is one real solution, right? It's a double root. It occurs twice. And if you picture this, this is a smile, again, because of the positive 2 in front of the x squared. So what you're essentially looking at here, well, let's not draw it with a y-axis because I know where the 0 is, but you technically don't. It's going to look like this. It's a smile that touches at one point on the x-axis, okay? And again, you weren't asked for the visual, but if it helps to have a visual, that's great. And on the last one, we can kind of make an educated guess that this is going to be the one where I get no real answers. All right, so my b squared is 4 squared, so 16 minus 4 times 2 times 3. Well, that's going to be a 16 minus a 24, which is definitely a negative 8. That's less than 0. So since it's a negative 8, there are no real solutions. And again, it happens that this graph is a smile because of the 2 in front of the x squared, the positive 2. So we're looking at a smile that never crosses the x-axis. See how there are no real solutions. And again, you didn't have to give me the visual, but it's kind of helpful to see it. All right, go ahead and try a P1. You can pause me if you want. I'm going to work through it, and you should go ahead and do the same scale we just did in E1. So again, my A is 1 here, right? My B is 2, and my C is also 1, and here's my A, B, and C, and here's my A, B, and C. And you do need to make sure that things are in this order with everything on one side of the equation and 0 on the other. So B squared minus 4AC, right, if we go ahead and do this for the first one, is going to be a 4 minus a 4 times a 1 times a 1, which is definitely a 0. So the answer is 0, and there's one real solution. And again, it happens that because there's a positive in front of the x squared, this is a smile. So we're looking at a graph that looks like this. B squared minus 4AC here, right? B squared minus 4AC is going to be a 16, right? 4 squared minus 4 times 2 times 5. What's a 16 minus 40? And if you want to find it, you absolutely can find it. That's a negative 24. But honestly, all you really care about is that it's less than 0. So there are no real solutions. And again, it's just coincidental that all the ones they're giving you right now are smiles. There's a positive in front of the x squared. So we're looking at a graph that looks like this. And then lastly, B squared minus 4AC is going to be a 9 minus a 4 times a 1 times a 1, which is going to be a 5, which is greater than 0. So since 5 is greater than 0, there will be 2 real solutions. And again, it happens that I was given a graph that is a smile because of the positive in front of the x squared. So what that's going to look like is, again, I didn't actually want to give you a y-axis because I'm not telling you where the roots are. I'm just telling you that there are 2 roots. So it's a smile with 2 roots. All right, let's move on. So let's talk about complex numbers. So whether it's possible to take the square root of a negative number is a question that puzzled mathematicians for a really long time. So in the 16th century, Italian mathematician Girolamo Cardano was the first to use complex numbers to solve quadratic equations. Then Leonhard Euler, and when you see this word that looks like Euler, that's Euler, and he's pretty famous, so you want to get used to saying it right, defined the imaginary unit I such that I is the square root of negative 1, and I squared would be a negative 1. In the 19th century, the theoretical basis of complex numbers was rigorously developed. So let's walk through what this means. So the imaginary unit I, right? So the imaginary unit I is defined as the square root of negative 1, all right? If you were given the square root of r, negative r is what they gave you here, right? That's the same as the square root of negative 1 times the square root of r, right? Which is the same as saying I root r. Okay, so the square root of negative 1 can be replaced with this I, and that's what it means, okay? For example, they give you the example of the square root of negative 4, right? So the example here, right, is that the square root of negative 4 would be the same as the square root of negative 1 times the square root of 4, right? Well, that's an I times a 2, so you'd get a 2I, right? Or if I gave you the example of the square root of negative 6, which they gave you here, the square root of negative 6 is the square root of negative 1 times the square root of 6. Well, you can't do anything about the square root of 6, but you can make that an I root 6. All right. Or root 6 times I. It's just important to be clear that the I is not inside the root. You've pulled that out of the root. All right. So let's go ahead and walk through an E2 and a P2 where we simplify roots. So I'm going to rewrite this as a negative 1 times the perfect square, which is root 49. So I get I times a 7. So this is a 7I, or I7. It's just weird to write it as I7. Now, 280 is not a perfect square, right? So I know that it's going to have a negative 1, right? But then when I look at 280, I really want to try and split it into the factors that are perfect squares. My first thought is that this is a 4 times a 70. Right, so that's a 4 times a 2 times a 35. This is the only perfect square in there. So this is going to be a root 4 times a root. I'm going to just leave it as a 70, right? So I'm going to get that this is an I and a 2 and a root 70 that can't be cleaned up at all. So you're probably going to see this as a 2I root 70. You could write it in any order as long as it's clear that the only thing inside the root is the 70, and that's kind of the deal. All right, so go ahead and pause me if you want. So this root negative 25 is a negative 1 inside a root and a 25 inside a root. So that's going to be an I and a 5. So you're probably going to write that as 5I. My eyes kind of look like little tents. I don't know why. It is what it is. Here, I know that I have this negative that's going to tell me that I definitely have an I, but then 90 seems to be a 9 times a 10. And 9 is the biggest perfect square I can get out of that because 10 is just 2 times 5. So I'm going to get that this is a root 9 and a root 10. So I seem to get an I and a 3 and a root 10. So you're probably going to see this as 3I root 10, although any order of those 3 items are fine as long as it's clear that 10 is the only one in the root. All right, moving on. So we're going to go ahead and use the quadratic formula to solve this, meaning it may factor, it may not factor, but you were asked to use the quadratic formula to solve, so do that first. There's a good chance that if you're asked to use the quadratic formula, it doesn't solve. Oh, fun side note, let's go up for a second. When you talk about the discriminant, if b squared minus 4ac is a perfect square, a positive perfect square, right, because you can't really be a negative perfect square, the thing factors. And it makes sense if you think about it this way, because if it factors, you should get like a nice, happy, rational number as your x's. So the only way you can get a rational number for your x's is if this square root is a perfect square so that it's not a square root anymore. So just throwing that out there, that if you want to see if something factors, you can actually do a quick cheat and do b squared minus 4ac. Cool. So let's go ahead and solve this. So x equals, right? So it's negative b. So my a is 3, my b is a negative 7, my c is a 5. So negative b would be a positive 7 plus or minus the square root of b squared will be a 49, because when you square negative 7, you get a positive 49, minus 4 times a times c all over 2 times a. And then I just clean some stuff up. So that's going to be a 7 plus or minus. My bad. Apparently I can't write like a functional human. Okay, 7 plus or minus. So this is a 49, right, minus what seems to be a 12 times 5, which is a 60, right? So I seem to get a negative 11. Yeah, that checks out. Over a 6. Well, that means that I'm going to have i's in my answer. So what's going to happen is that this root negative 11 is actually a root negative 1 times a root 11. So I'm going to get that the answer is 7 plus or minus I root 11 all over 6. And that's my answer. It also means that if you have a calculator program to do this, you're going to get an error because your calculator is set to only deal with real numbers unless you change some settings. So the other way that you'll see this written sometimes is a 7/6 plus or minus I root 11 over 6, where this is the real part, and we're going to talk about that more moving forward, and this is the imaginary part. So real component and imaginary component, so we'll talk about that moving forward. All right, so go ahead and try P3, and then we'll move on from there. So negative b plus or minus the square root of b squared minus 4 times a times c all over a 2 times a, right? So I'm going to get that this is a negative 5 plus or minus. So this is a 25 minus what seems to be a 48, right? So I think I get a negative 13 in there all over a negative 8. So this negative 13 is going to be a root 1 times a root 13, which will be an I root 13. So my answer is going to be 5 plus or minus I root 13 all over negative 8. That answer's fine. The other option is I've seen people want to cancel the negatives. If you wanted to factor a negative out of everybody, this essentially becomes a minus over plus instead of a plus over minus. So the other way you might see this is this. It wouldn't be wrong if you didn't flip the plus over minus and the minus over plus. It's the same answer. And the other way you might see it is if you split it up into 2 separate fractions, right? So either this or this one split up into 2 separate fractions. Honestly, I'd probably stop here though. All right. Cool. So let's talk about some complex numbers. So a complex number is any number that can be written as a plus bi, where a is the real component and b is the imaginary component, or real part and imaginary part. A and b are real numbers. So the form a plus bi is called the standard form of a complex number. Real numbers are complex numbers for which b is 0, right? So a real number has no imaginary part, and a complex number is called a pure imaginary number if the a part is 0, if it only has a bi. So the trick here is that real stuff has to equal real stuff, and imaginary stuff has to equal imaginary stuff. So you're given 7x minus 2iy equals 14 plus 6i. So this is the real part on this side. it has to equal the real part on the other side. So if I want to set up an equation for my real components, 7x has to be 14, so x has to be 2, right? My imaginary part has to equal my imaginary part, right? So the imaginary parts have to be equal. So negative 2iy has to equal 6i. Well, that gives me that negative 2y equals 6, because those are the coefficients of the I, right? They're the part that aren't I, which means my y is a negative 3. All right. So one last one, and then we'll stop this and we'll have our next video in a second. So same idea. You're going to set the real stuff equal to the real stuff, and the imaginary stuff equals the imaginary stuff. So real would be 2x equals negative 8. So that gives me that x is negative 4. And my imaginary part is that 3iy equals 10i. So 3y must be 10, y must be 10 thirds. All right, and that is it for this video.